Hello, I would suggest that you pause the video and try these two warm-up problems. So here are our solutions. Once again, the first one was a rational equation. So remember, once you solve for x, you must check your solution. In this case, it didn't work, so that's why we have that empty set. In the next one, just make sure you're reading the directions very carefully as to what the question's asking for. It said in which year. So once you solve for x, that wasn't your final answer. I wanted a year for the final answer. Today we are moving on to section 1.5, which is about quadratic equations. Our specific objectives today, we are going to solve by factoring as well as the square root property. Let's define what a quadratic equation is. A quadratic equation in x is an equation that can be written in the general form ax squared plus bx plus c equals 0. So that's what it means when we're talking general form. Everything's to one side, it equals 0. A, b, and c are real numbers. A will never equal 0 because if it does, the x squared term cancels and then we don't have a quadratic equation. A quadratic equation in x is also called a second degree polynomial equation in x. Okay, so anytime it is degree 2, we are talking quadratics. So let's talk about how we would solve by factoring. Here are steps. If necessary, rewrite the equation in general form. So we want everything to one side. We want it to equal 0. I do always want the x squared term to be positive. Once everything's moved to one side, we'll factor completely. We'll then apply the zero product principle. So basically what that means is once you have everything factored, you set each factor that contains a variable equal to 0. Once you have all those equations equaling 0, we'll then solve the equations, and then it would be a good idea to always check solutions into the original equations to make sure that you solved it correctly. Let's take a look at these examples. So in the first one, 3x squared minus 9x equals 0 is in general form. It's all to one side, it equals 0. So that means that we can start thinking about factoring. So remember, first step is to always look for a GCF. I see that those two numbers, 3 and 9, definitely have a number in common. They have a 3 in common. Both of those also contain variables. So x is what they both have in common. So 3x is my GCF. When I factor that out, that leaves me with an x minus 3. This is still an equation, so it still equals 0. By factoring out that GCF, what I have left over is not going to be factorable any further. So now that means we can move on and I can set each factor equal to 0. Because my GCF contains a variable, I get to set 3x equal to 0. If it was just a 3, I would not set that equal to 0 because 3 doesn't equal 0. So there has to be a variable involved there. The other factor of x minus 3 equals 0. Now I can start solving for x. So I can divide both sides by 3, and so that tells me 0 divided by 3 is 0. Over in the second equation, I can add 3 to move that over, and 0 plus 3 is 3. Notice that I have two answers. Once again, you can always plug those back into the original equation and double check that the left side equals the right side. It will. Notice if I plugged in 0, anything times 0 is 0. So 0 minus 0 equals 0. That checks out. If I was to plug in the 3, 3 squared is 9. That gets multiplied by 3, so the first term is 27. Over here, when I plug in 3, 9 times 3 is 27, and 27 minus 27 is 0. Notice that I have two answers, and that should be the case. If we're solving a quadratic, which is degree 2, that exponent 2 tells us that we should have two solutions. If I look at the next one, it is in general form, which is good. Notice that if I start looking for a GCF, this time I don't see anything in common. If there is no number in front of the x squared, that tells us that, remember, we want to find numbers that multiply to negative 14, but add to negative 5. So it multiplies to the last, but adds to the number in the middle. Each of my binomials is going to start with an x, because once again, x times x is x squared. So what multiplies to negative 14 but adds to negative 5? That would be negative 7 and positive 2. Now I get to set each of those equal to 0 to finish solving for x. So notice that I have to add the 7 as well as subtract the 2. and I get two answers, a positive 7 and a negative 2. And once again, I can go back, plug those values in, and verify that the left side does equal the right side. And I'm telling you right now that it does, so we're good. In this last example here, notice that it is not in general form. Because the x squared term is on the left and it's positive, I want to keep that where it is. So that tells me I have to move the terms from the right over to the left. So I had to subtract 1. So that gives me 2x squared plus x minus 1 equals 0. Looking for a GCF, I don't see anything in common. Because there is this lead coefficient, remember, think about all the ways to multiply to that first number, and then think about all the ways to multiply to the last number. Luckily for us, those two numbers are prime numbers. So I know that I'm going to start with a 2x and a 1x in each of those binomials. I know I'm going to end with a 1 and a 1. Because I need to multiply to a negative 1, but I have to add to a positive number, I know I'm going to have one of each sign. I'm going to want the positive to go here and the negative to go there. Because if I check it out, notice that this turns into 2x. This will turn into negative 1x, and add those together, I will get this positive 1x in the middle. So once I've done my guessing and my checking, I know that I get to set each of those equal to 0. Oops. So 2x minus 1 equals 0, and x plus 1 equals 0. Now I can start solving for x. Notice I have to add 1 over, and then that gives me then 2x equaling 1. So I have to divide by 2, and so one of my answers is a fraction. It's 1/2. Notice on the other side, I just have to move the 1 over by subtracting. And so always, once again, you can check your solutions to verify that it is correct. You should have two answers, 1/2 and negative 1. So I would suggest you pause the video, try this checkpoint problem. Okay, notice that you had to first get it into general form. There was no GCF. It involved us doing guess and check, and we ended up with two solutions. All right, the second property is solving by the square root property. So let's take a look at these steps. We want to first isolate the x squared term by itself. So to do this, we think about adding and subtracting numbers that are on the same side as the x squared first, moving those away, and then we'll multiply or divide numbers that are attached to the x squared term. We'll then use the square root property, meaning that if I have that square term isolated by itself, I take the square root, but remember, that's going to get you two answers. So you can write them separately, or I like to just use this plus or minus sign in front, and it shows me that I have two solutions. We always want to make sure that if we get a radical for an answer, we simplify as much as possible. So let's take a look at these examples. We're going to solve by the square root property. So notice that in this first case, I have two numbers that are on the same side as x squared. Notice that there's no x term, and that's why that indicates that we want to do the square root property. So we want to add the 21 over to the other side. That gives me 3x squared to equal 21. We got to still get the x squared by itself, so I'm going to divide by 3. Now x squared equals 7. And because now the squared term is isolated by itself, I'm going to take the square root of both sides. Taking the square root of a square is just going to give me now x by itself. Anytime I take the square root in an equation, I get two solutions, both positive and negative. Square root of 7 is not going to be a perfect square. You're not going to be able to break it down any further. So positive and negative square root of 7 would be my solutions. Same idea with the next one. Notice that there are no x terms, so we can do the square root property by isolating that squared term by itself first. So I'm going to subtract the 45. That gives me 5x squared equals negative 45. I'm going to divide both sides by 5. So now x squared equals negative 9. Once again, we have the squared term isolated, so to undo a square, we're going to take the square root. That will give me x by itself. Over here, notice that we have a negative number underneath a radical. We do have a solution. Remember, we will have two answers, but because we are dealing with a negative, I know that I'm going to have an imaginary number. The square root of 9 is a perfect square. Square root of 9 is 3. So my two answers, x equals both positive and negative 3i. In the last one, it already has the squared term isolated by itself because notice that what I have in parentheses, the whole thing is being squared. So if there were any numbers outside of the parentheses on that side, we'd want to move them to the other side. But once you have that set of parentheses squared by itself, what we want to do is we want to take the square root of both sides right away. Once again, taking the square root of a square, that just leaves you what was underneath that radical. So just the 2x minus 1. Over here, because I took the square root of both sides, I do have two answers, so both positive and negative, and 16 is a perfect square. That would turn into 4. Now I want to start solving for x. So I'm going to add the 1 over to the other side. So now 2x equals 1 plus or minus 4. So what I'm going to do here is I'm going to show you the fact that because we were able to take that perfect square and get 4 and there's no radical, I want us to understand that we technically have two different equations. We have 1 plus 4, so that would give me 5. And we also have 1 minus 4, which would give me negative 3. And so then I can finish solving and I'll have my two solutions. I just have to divide by 2. Because 5 halves doesn't simplify any further, I can leave that fraction as it is. And then I'll divide by 2 over here. And same idea, negative 3 halves does not simplify down any further. I'll keep it as that fraction. There we go. There are solutions. If that 4 wasn't a 4, so say it was like the square root of 17, so then I'd have 1 plus or minus the square root of 17. Well, then I wouldn't really have to break it up any further because I didn't have like terms that I could combine. But if you do have perfect squares, I do want you to combine to its fullest, please. So once again, I would suggest that you pause the video and try to solve. All right, so notice that I took the square root of both sides, got two answers when I took the square roots. Square root of 11 is not a perfect square, so that had to stay as a radical. And then I moved the 5 over by subtracting. I like to keep that the radical second because of that plus or minus sign in front. Technically, if you have plus or minus the square root of 11 and then minus 5, you do have the same answer. All right, so that is us solving quadratic equations by both factoring as well as the square root property.